Good morning, everyone. Thanks for being here on this lovely May morning. And we're going to start our last session with Yimu, who is currently at Singapore.
Thanks. This sounds good. Okay. First, I want to thank the organizer for organizing such a great workshop. So today I'm going to talk about recent work we posted about 2 months ago with Stephen Yan, who is currently in the audience, and Sagar who is in Santa Barbara. Oops. Should I?
Maybe hit play.
Wait, okay. Yeah. So I realized I put a somewhat esoteric topic. So what I'm really going to talk about is, oops, how to switch.
If it's not working, you can just advance it here.
Okay. Okay. Well, what I'm really going to talk about is just a theory of decoding in the Torah code with coherent error. This is good. So if a quantum computer is ever going to be made, it has to function in a noisy environment. In the presence of noise, if one wants to maintain coherence and carry out the fault-tolerant quantum computation, an essential element is the quantum error correction. From yesterday's talk, we have learned that there are two main strategies for carry out quantum error correction. One is the active error correction based on a non-equilibrium protocol by performing measurement and feedback and implementing feedback in the quantum device. And there's another path towards error correction through the so-called passive error correction, which we start to know how to write down a scheme in three dimensions. So today I'm going to focus on the first type of error correction, which is slightly more understood and we have more experimental progress on, which is the active error correction. So recently here we have seen many exciting progress in the quantum industry. In particular, one particular successful step towards error correction is now we can realize topological quantum memory in various leading experimental platforms, including superconducting qubits, ion trap, and atom arrays. So in these platforms, we are now able to realize quantum error correction in a particular type of quantum memory people have been studying in the past 20 years, so-called topological quantum memory. In this type of quantum memory, it has the nice property of encoding quantum information robustly against the arbitrary type of local noise. So a paradigmatic example of such kind of quantum memory is the so-called 2D surface code proposed by Kitaev in about 30 years ago. So the 2D surface code is a stabilizer code on a two-dimensional lattice, and the stabilizer code involves four body check operators, and you can encode 1 qubit logical information if you put it on this open boundary condition. And in particular, surface code has the nice property of having a high error threshold, which is being shown in about 20 years ago. So let me before we move on, let me just briefly recap a little bit about what is the active error correction scheme people use in order to retain the quantum information in the Torah code. So usually, if you encode quantum information in the Torah code, and as I said, due to the coupling with the environment, some local error can happen in the encoded state. The local error are most generically described by the local quantum channel. And the active error correction scheme starts by measuring the stabilizer in the system and observe the possible excitation created by the underlying error operators. And based on the syndrome information one collects, we can apply the recovery string to remove the syndrome, and hopefully we can go back to the code state and maintain the encoded quantum information. And realistically, we hope to run this thing repeatedly in order to maintain the information for a long time. Okay, so this problem has been studied a lot in the context of surface code. However, I want to point it out one thing, which is the local error model people consider in the study of quantum error correction can be broadly divided into two different categories. One, the first type I would call incoherent error. Those are the error channel that does not create coherences between different anion configurations. It is a quantum channel that creates incoherent mixture of surface code with different anions. There's another, there are many examples of this. Could be local dephasing, local bit flip, or depolarization channel that we are most familiar with. There's another type of error that can also happen in experiment, which is very relevant. It's called coherent errors. These types of errors create coherent superposition between the surface code with different anion configurations. The simplest example of that could be just a single qubit rotation. So the decoding problem in the surface code with incoherent error is a problem that has been well understood and pioneered by Denis Preskil-Kitaev. And in this problem, I'll briefly recap this problem just also to define the object of interest in today's talk. So let's consider the simplest case, that is, you have a surface code subjected to the say the local dephasing, as I write in the previous slide, and what the decoder is trying to do based on the in the error correction scheme is you start from the noisy surface code and try to measure the syndrome. Based on the syndrome configuration in the surface code, there are usually different error string that are compatible with the syndrome configuration. And for the decoder, from decoder's perspective, the goal is to figure out which recovery string to apply in order to remove the error syndrome observed in the system. So in this case, there are two homologically different choice of the error string, which are labeled here, for example, C1 and C2. The goal of the decoder is to figure out which error string from which homology class has the higher probability and apply the recovery string belong to that homology class in order to go back to the encoded state with a higher fidelity. So the goal of the decoder, if you want to run an optimal decoding strategy, the task for the decoder is just trying to evaluate the probability of syndrome created by error string in a certain homology class. This quantity I would call Q alpha S consistently throughout today's talk, and this is the main quantity of interest, and that will turns out governs everything in the analysis of optimal decoder. For this well-developed story, people has known that the decoding fidelity, which is governed by the probability Q alpha S, is going to undergo a phase transition when you crank up the error rate P. Oh, by the way, for the audience that are not in the community of many-body physics, today I'm a many-body theorist. I'm mostly interested in the behavior in the thermodynamic limit. So today I'm going to so decoding fidelity in the surface code is a quantity that is going to show a many-body singularity as you take the thermodynamic limit. So in this case, you will see that the decoding fidelity undergo a phase transition from when P is less than a threshold value PC to a regime that fidelity essentially dropped to a suboptimal value when P is greater than PC. There has been a full-fledged theoretical understanding of this decoding transition in the case of incoherent error. People formulate this Q alpha S as the partition function of so-called random non-IC model with Nishimori line, and when you crank up the error rate, there can be a phase transition between the ferromagnetic phase to the paramagnetic phase, and the decoding fidelity is related to some excess free energy of inserting a defect, which essentially see the phase transition in this effective Stamac description. And that will explain this many-body singularity we see in the previous slides, and explain the underlying mechanism of the phase transition in the presence of incoherent error. Okay, as I mentioned, there's another class of error which we call coherent error. These are the type, for example, you should keep in mind the simplest example of coherent error is just single qubit rotation acting on every single qubit. For this type of, for decoding in the surface code with coherent error, people actually start thinking about this question only about 10 years ago. In this problem, the difference is that when you try to evaluate the probability of syndrome created by error string belonging to a homology class alpha, this Q alpha S instead of in the previous slide given by a partition sum of positive real number governed by a Boltzmann weight of Stahl model. In this case, you will see the Q alpha S is going to be given by the sum of complex numbers. And if for this reason, Q alpha S has no Stahl description. So that prevents you to doing a Monte Carlo, for example, efficient classical Monte Carlo simulation to figure out where is the threshold. A central question of interest is the first order question one can ask is what are the possible phases in the presence of coherent errors? So about a year ago, we wrote a paper with Sajjad, who is currently a postdoc at Harvard. We managed to show that this transition in the 2D surface code with generic type of unitary error, which is a particular type of coherent error, actually maps to the phases of 1+1D dynamics in the with unitary and measurement in the presence of additional Z2 symmetry. And in this case, there has been a previous study in the context of monitor dynamics and what are the possible measurement-induced phases. They have been well understood what is the dynamical phase transition in such kind of dynamics. Turns out you can relate the encoding phase and the information loss phase to the symmetric phase and symmetry breaking phase in this 1+1D dynamics. And furthermore, the dynamics also have another transition governed by the seen by the entanglement in the steady state dynamics. There, the entanglement in this dynamics actually manifests as how hard it is to implement this error correction scheme. We show the possibility of some coexistence of this volume law entanglement and the ferromagnetic ordering, which translate in the error correction language as a phase that encode quantum information, but recovering quantum information using this particular decoding algorithm is actually practically hard. This was the story for the decoding in the surface code with general unitary error. However, in today's talk, I'm going to talk about decoding in the surface code with a particular type of unitary error, which just consists of single qubit rotation acting on every single qubit. So this is the simplest type of coherent error that also has been studied in the previous work. Also has experimental relevance as being because this single qubit rotation in the experiment can originate from, say, an uncalibrated magnetic field or a tilted measurement basis, for example. Usually as and also I have to say, like, this is the simplest type of coherent error, but it's not the generic case. But often as a theoretical physicist, we usually find that the simple and non-generic case is usually have a more sophisticated and analytically trackable theory. However, the generic case, we usually cannot do anything analytically. So I'm going to show you we have a theory of how to analyze the decoding problem in the presence of this type of error. So in this case, as I alluded in the previous slides, in this case, the key is Q alpha S, which is the probability of error string from a certain class. It actually can be written formally as a partition sum over some both complex Boltzmann weight. You can translate this partition sum as the partition function of a random bound Ising model instead of with a real coupling, but with a complex coupling, which is written here with J depending on the rotation angle theta. This has been figured out in the previous works. Okay, there's another interpretation of this complex Boltzmann weight in terms of the fermion language, which hopefully makes some connection with the disordered fermion problem. So there's people in this very nice work by Cambridge group. They have shown that the probability, this Q alpha S, can be written as the absolute value square of this partition function Z, and this complex random bound Ising model Z can be written in terms of transfer matrix. And the transfer matrix in the fermion language corresponding to a free fermion transfer matrix. It turns out that this free fermion transfer matrix belongs to the defines a scattering problem in 2D, and the scattering problem belongs to the class D, and defines a Chocker-Coddington network model in class D. So this make connection between the quantum error correction and the disorder fermion problem in 2D. The same network model actually emerged in the description of Anderson localization problem in class D, and which is the fermion problem with only particle symmetry. In the Anderson localization problem, it has been well known that I think there's a typo here. Known that in this case, in the Anderson localization problem, there can exist a metal phase, and there can also exist a multiple insulator phase, actually more than two. When you tune certain disorder parameter, you can induce transition between metal and insulators. Then the question one can ask is, now that the decoding problem bears a similar description with the disorder fermion problem, when you tune theta, whether one can induce a similar metal to insulator transition in the quantum error correction setup. There has been numerical evidence in these two papers. However, in today's talk, I'm going to show you there's some subtlety that needs to be clarified in this problem. In particular, I'm going to show you that this the existence of metal to insulator transition heavily depends on the decoder's knowledge of the underlying error model. So this is something I kind of sweep under the rug, but if we take a step back and think about what is the setup for the decoding is always done in two steps. First, you prepare your quantum encoding state in your quantum memory in your experiment, and some error happens. In this case, the error is the unitary rotation. And there's an observer that measures the syndrome and passes the syndrome to the decoder. So what decoder is trying to do is trying to guess what is the homology class of the error string based on decoder's prior assumption of what is the error model. So decoder has its own estimate on what is the value of theta. It turns out the phase diagram heavily depends on whether the decoder's estimation of theta exactly agrees with the true rotation angle theta or not. What I'm going to show you in today's talk is if the decoder knows the rotation angle theta, which I would call optimal decoding, there does not exist a metal phase. Turns out our numerical evidence suggests that there is a decodable phase all the way up to the maximum rotation angle theta equals pi over 4. However, in the case of suboptimal decoding, when the decoder has an incorrect prior assumption, there's an insulator to metal transition when you crank up the rotation angle theta. So here is an outline of today's talk. So I thought it would be good to have a brief walkthrough of the theory we developed in the paper. So today's talk is going to break up into a few parts. So first, I'm going to formulate this decoding problem in terms of formulate a replica sequence that describes the decoding problem. And I'm going to show you there is a sequence of a nonlinear sigma model that governs the decoding fidelity, which is the central quantity of interest in this in this problem. And then I'm going to show you there's some predictions of this arise from the nonlinear sigma model and how it agrees with, and we verify these predictions using our numerical simulations. So yeah, as I mentioned, the decoding is done in two steps, and I call the true distribution of syndrome Q in today's talk, and I call the estimated distribution of syndrome according to decoder's prior knowledge, I call it P. So for the optimal decoder, Q equals P, and the decoding for today's talk, for the ease of analytic analysis, I focus on one particular type of optimal decoder. There are many optimal decoders. They are all asymptotically the same. I'm focusing on the decoder I call Bayesian decoder, where the decoder applies the recovery string in class alpha according to the according to the conditional probability Q alpha S, the decoder assigns to the class alpha. So the success probability is given by the Q alpha S times P alpha S of the decoder. So that gives you the decoding fidelity, which is the quantity one wants to consider. An important thing is in this expression, you will see that for the particular syndrome configuration S, the quantity you want to evaluate is a nonlinear function of the underlying quantum state. So naively, the averaging over distribution, syndrome distribution cannot be done very easily. So one needs to invoke the replica trick in order to analyze what is the decoding fidelity. So this is a little bit technical, but the point is we can formulate a replica sequence. One second. Formulate a replica sequence for the decoding fidelity. Yes.
So how do I see that the square is the right choice to get your highest threshold?
Get the highest threshold. This is a bit technical, but there's a proof that this Bayesian decoder has the same threshold as maximum likelihood decoder. That is known to be the optimal decoder. We had the proof in one of appendix.
Thanks.
Sure. This is an optimal decoder given the measurement sequence that you designed.
Yes.
There could have been a more optimal POVM, maybe.
That is true. In this case, there's a trivial POVM, just the rotated POVM.
Yeah.
But I think the setup is more motivated from an experimental perspective. Only the measurement in one basis is being well calibrated. Okay, the point is you can formulate this decoding fidelity in terms of a sequence of decoding fidelity. I call it Fn. And this you can write down this Fn in terms of some quantity, which is phi. And this phi is related. I'm going to show you this phi is going to be related to the expectation value of inserting a symmetry defect in an effective model. I call it Z0. And this Z0 is going to be the nonlinear sigma model which we derive. Okay, to summarize what I'm going to show you in the next two slides is I'm going to show you that this Z0, which essentially govern the replicated decoding fidelity, is given by a partition function of a nonlinear sigma model with matrix field Q that belongs to the target space SO 2n plus 2 mod UN plus 1. And this phi is the twist expectation value by inserting a twist in this direction in the sigma model. So to motivate this derivation, so we need to first thing one needs to figure out is what is the symmetry of this problem, which is of this partition function Z0. It turns out here there's a subtlety I didn't emphasize at the beginning of the talk, but for this part of the problem, we consider the surface code on the square lattice. Later on, I will show you the lattice structure actually matters for the effective theory we derive. So on the square lattice, you can do some manipulation and show that you can write down Z0 in terms of the 2n plus 2 copies of the complex partition function Z. Usually, you just have the n plus 1 copy of Z and n plus 1 copy of Z star. For the square lattice, you can do some sublattice transformation to convert Z star to Z. But the point is, on the square lattice, Z0 is given by Z to some power of 2n plus 2. And for each copy of Z, one can write it in terms of some transition amplitude in the Chalker quantum network model with the transfer matrix generated by Majorana bilinear. Here, the problem will have an enlarged continuous symmetry because now we replicated a free Majorana transfer matrix for 2n plus 2 times, and each one of them has the same disorder realization. That will lead to an enlarged rotation symmetry among the 2n plus 2 copies of Majorana. And that is essentially what is the symmetry of this governs this partition function Z0. And this motivates the following derivation of the field theory. So we always, another thing I need to emphasize is the decoding problem has a special angle, which is theta equals pi over 4. At that point, the network model has no backward scattering. So it's a ballistic metal from the perspective of this disorder fermia. And at this point, one can write down Z0 as very simply as a free theory with with chiral Marana mode moving to the left and right. And when you perturb away from pi/4, the averaging over syndrome configuration will generate inter-replica interaction. And the symmetry we identified in the previous slides motivates us to derive the effective field theory by in the usual as in the usual condensed matter textbook, by writing down path integral doing the Haber-Strauss-Hanovic and find the saddle point and expand around the saddle point. And this eventually leads to this sigma model description of the decoding problem when you are close to the rotation angle pi/4. And we are going to analyze what is the behavior according to our field theory knowledge. Any question? Okay. The story for suboptimal decoder is more or less the same, and the only difference is now because the decoder has a different prior knowledge of the rotation angle theta, so P will be different than Q, and that will lead to a slightly different symmetry of the problem. This partition function, which used to call Z, and now I call Y for the suboptimal decoder, will only involve n copy of P and 1 copy of Q. So the Y will in the end exhibit a reduced symmetry, which is O2 by O2n. Yes. So this leads to a effective theory. Add additional term to the effective nonlinear sigma model description, which is a local potential term that breaks the symmetry. And this term is relevant, and when you go to a larger and larger scale, and the effective theory will eventually become a sigma model with a reduced target space SO2 and mod UN. Okay, this is probably the most important conclusion from the sigma model. So now we see that the optimal and suboptimal decoder are just related to the different replica limit of this sigma model with target space SO2 and mod UN. And turns out the field theory calculation tells you that the metal fixed point has a different stability in these two different limits. So for the optimal decoder in the limit n to 1, the metal fixed point has a coupling that is marginally relevant, which will flow away from that. However, for the suboptimal decoder, the RG flow, the coupling is marginally irrelevant, which will give you this metal phase. And when you tune the coupling constant G, or effectively the rotation angle theta, you will have the transition between the two. The undetermined part is here. So when you have the optimal decoder, we know it will flow away from the metal fixed point, but we know there exist multiple different insulators. So the question is, what is the phase diagram here? There could be two situations. One is it is always one insulator phase connected to the theta equals 0, which indicates that the entire regime is decodable. There's another situation you can have a transition between two insulator phase, and one is decodable, one is not. That's another possibility. And this we answer using in terms of the numerical simulation. So it's okay. The thing is, we compute the fidelity of optimal decoder, and as a function of theta, you see the fidelity. First of all, okay, this is a bit puzzling. I'm going to explain. But the fidelity, you see the fidelity is 1 below a certain value. However, it becomes something that is smaller than 1 when theta is large. However, the important point is if there were a transition, you are going to see the decoding fidelity cross at a single point, if you assume the critical point is a CFT. However, in this case, we don't see that. We see no signature of the transition. So that makes us believe the situation, the phase diagram should be the second. There's always this decodable phase all the way up to theta equals pi/4. Now you may ask me, then what is going on here? It turns out this is I'm going to explain in the next slides. This is exactly the finite size effect that is going to predict. You are going to predict when you flow away from the metal fixed point in the sigma model. So sigma model actually, okay, then going back to this formula is a bit technical, but you can show that the sigma model fidelity has an interesting behavior when you fix the aspect ratio and trying to ask how does the fidelity scale with this renormalized coupling at at the scale L. So there's a reverse trend reversal when you consider the kappa much greater than 1 and kappa much less than 1. So when you sit at some intermediate kappa, you may see that the decoding fidelity just does not depend on theta too much when your system size is at some intermediate scale. That is what explains here the seemingly a plateau that you observe in this behavior. So this is exactly what you should expect when you flow away from this metal fixed point. What we believe is if you are able to simulate a very large system size, the fidelity will eventually probably go to 1. However, that is beyond the access of current simulation. We also have, I probably don't have time, but we also have some prediction on the fidelity of suboptimal decoder. You see that there's some transition with fidelity cross at a single point, and there's some prediction that verifies our prediction. Okay, there's some other check on our theory. I'm going to finish in 2 minutes. So the theory in terms of you can simulate the conductance, that also agrees with the prediction of this from the sigma model. Okay, one last thing is I want to emphasize that if you put the surface code on the triangular lattice and create the syndrome on the vertices of the triangular lattice, which is not bipartite, then in the end you get a different sigma model with a target space that's just given by SO. And in this case, both the optimal and suboptimal decoder will have a metal to insulator transition, which means when you crank up the theta, you will eventually enter into a metal phase that is not decodable. Okay, so here's the summary. I hope I convinced you that there's a difference between the optimal and suboptimal decoding when you consider the surface code on the square lattice, and we use this effective theory to make a bunch of prediction on the quantity that people care about and examine it using the numerical simulation. There's a bunch of outlook. I don't have time. If you're interested, you can also talk to Stephen or me after the talk. Okay, thanks.
And for a couple of questions. Well, let me start by asking the ballistic phase specifically, which seems like a sort of so you're saying with the optimal decoder you see this sort of single point of theta. So what's special about
okay.
ballistic versus being a metal?
Oh yeah. It's ballistic is only a point. That is a ballistic matter, but this metal is a thermal metal.
Right.
So the difference in terms of decoding is at this ballistic metal point, you will actually see the decoding fidelity oscillate with the aspect with the different L and the T. So it's a big because you can see that this evolution in the network model is essentially coherent. So you will see some oscillation in the oscillatory behavior in the fidelity, but this thermal metal is really it is a correct prediction of the sigma model when your system size is above this mean free path, where basically the incoherent phenomena kick in, and you will see the decoding fidelity in this thermal metal phase will be something something that is below 1, which is what we call a non-decodable phase. Okay, yeah, maybe Alex.
Excellent talk. First of all, I missed where characteristic of suboptimal decoder enters the game. The width of your
the what?
I mean, your suboptimal decoder approximate your theta.
Yes.
With some fidelity, whatever.
Yes, call it
uncertainty, right? So where is this characteristic in your phase diagram?
There. Yeah. So the transition threshold theta c will depends on this. Depends on the estimation, which is the precision, which is epsilon. Okay. And in terms of the field theory, this precision comes in as here, which governs the strength of this relevant perturbation. Basically tells you at what scale you start to tell the difference between suboptimal and the optimal decoder.
Okay, and in practical terms, well, do you understand how wide should be your uncertainty to have a reasonable threshold?
To have a reason? Oh, you mean to have To have a threshold that is significantly
Right,
different than
right.
pi over 4.
Yeah.
Oh, that we don't know. I don't know how quantitatively how that behaves. I believe there's a.
One last question.
Oh, okay.
Okay, maybe in the interest of keeping things on time, let's move on to our next speaker. Did you have a question?
Yeah, yes. So in our paper, we show that there is a difference based on the parity of the stabilizer weight in the post-mesh operation. And that's very interesting that in the triangular lattice surface code, you find quite a different behavior, or one of the triangular stabilizers are not weight.
Oh, but if you on the square lattice with even weight, also first of all, the theory for the square lattice on the surface on the square doesn't depend on whether it's odd weight or even weight, because we care about the fidelity that is after this Pauli recovery. Even if the logical qubit is just undergo a unitary rotation, the fidelity is not subject. No. Guaranteed to be one.
Related to the calculation threshold, then we can talk about that.
Yeah.
Okay, we're ready to start our second talk. So we're going to continue with Sam Garratt, who's currently at.
Yeah, thanks to the organizers for putting together this workshop and for the invitation to speak. So I'm going to be talking about some work in collaboration with Max McGinley, currently at Cambridge, moving to UBC in the next month or two. So this talk is really about identifying the kinds of quantum systems where we need quantum simulation. One of the reasons that we need quantum simulation is that many-body quantum systems are quite hard to describe. And one of the reasons that they can be hard to describe is because they're entangled. So if we imagine that we have a bunch of interacting particles, a pure quantum state of those particles is some superposition of their configurations. And of course, individual particles here do not have well-defined states. And therefore, we cannot describe the state of a whole many-body system as the composition of the set of states, the composition of the state of the individual particles, right? So because you can't get away with a description of your quantum system in terms of the states of individual particles, in general, you're going to need an amount of memory on your classical computer that scales exponentially with the particle number just to write down the state, okay? So this is an ancient problem and motivated quantum simulation some time ago. So the idea, of course, is that you're supposed to take some highly controlled quantum system and use that highly controlled quantum system to simulate the one that you're really interested in, right? So the scenario we have in mind is that you've done some experiment, say on a complicated molecule or a quantum material. I'll be thinking more about the latter. And then having observed some property of this material, you want to understand it. And in order to understand it, what you do is you set up some simulation. So we're now getting close to a situation where we can start doing this. And so we have to ask, okay, well, how is it that we look at the quantum materials we have access to and identify which of them are unlikely to be simulated efficiently on a classical computer? So today, what I'm going to be talking about is how it is you see that entanglement is a necessary part of a description of a many-body quantum system from a conventional condensed matter experiment. Okay, so the first point is that when we're thinking about an experiment on a quantum material, we're typically thinking about a system in thermal equilibrium. So the question I want to ask is when it is that entanglement is a necessary part of our description of a thermal equilibrium state of a many-body system. So what we should have in mind is that we had some system that was interacting with its environment, say a bunch of phonons or whatever, for a long period of time, and that at the time we come into contact with this system and do our experiment, it is described by some thermal state with respect to some Hamiltonian that we don't necessarily know. We just know its temperature. So one result from the computer science community a couple of years ago that motivated essentially all of what I'm going to be talking about today is that if you look at thermal states of interacting spin systems, it turns out that above some order 1 temperature, there's actually no entanglement at all. So this was very surprising at the time. There might be some short-range quantum coherences, but at high temperatures, you really don't need to think about entanglement at all to describe a thermal equilibrium system. So what's very striking about this result is not only that there's no entanglement, but also that at these high temperatures, you can efficiently calculate all correlation functions in these thermal states, okay? So this is actually how they show that there's no entanglement. They show that there is an efficient classical Monte Carlo algorithm that allows you to compute correlation functions, okay? So there's no entanglement at high temperatures. And you might ask, well, how is it that we miss this? Because we've been thinking about thermal states forever, and we've been thinking about entanglement in many-body systems for the better part of 30 years. So how is it that the kind of computer scientists have just waded in and figured out that there's no entanglement at high temperatures? One possibility is that maybe the absence of entanglement at high temperatures is not really relevant to physical properties, okay? Maybe it's really just a computational property that we wouldn't be able to see in a standard experiment. What I'm going to show you throughout this talk is that is actually not the case. And the entanglement that emerges at low temperatures in many-body systems has clear signatures in very standard correlation functions. Actually, before I move on, are there any basic questions on the setup? Okay, I just want to know how to see that this thing here is entangled. Okay, so what is it that we see in our experiments on finite temperature systems? So if we imagine that we were focusing on a bunch of spins, they're not in isolation, they're interacting with everything around them, other things in the material and maybe some external driving, whatever. So what we might observe is that the autocorrelation function of our spins relaxes in time, okay? This is a kind of caricature of what you'd see in an experiment. So I shouldn't have mentioned driving, so we should really be thinking about a system that is kind of just interacting with its environment and coming back to equilibrium after we perturb it. And a kind of story we tell ourselves about why we would observe relaxation like this in experiment comes from a really classical picture. What you might say is that you have some spin configuration, and thermal fluctuations cause flips of the spins. Gradually, the spins explore the space of all possible spin configurations, and your description of the system is then agnostic to kind of when you've looked at these spins, and so the average state over time in this kind of classical picture is some thermal ensemble, okay? So a really important point, which is going to really be the core of the connection between our observations and the entanglement that might exist in thermal states, is that really, this classical stochastic dynamics is just a story, and in principle, everything is supposed to be described by some unknown quantum Hamiltonian, right? And those thermal fluctuations maybe were coming from interactions between our spins and phonons, but really the spins, the phonons, everything around them is described by some unknown quantum Hamiltonian. This seems like a pretty abstract point, but it's going to be very important later.
Just maybe a question about the setup I should have asked. But clearly, the system and the phonons are highly entangled. But is this material to our description of the system? Because we obviously can describe it by some fictitious Langevin dynamics, and it describes all these correlations well.
Maybe it'll describe the qualitative correlations well, right? So it might be that you can write down some Langevin dynamics that, describe, it gets the right power laws and so on. but it might be that it's quantitatively off. And in fact, you might be able to write down a classical Langevin dynamics for the spins that actually perfectly approximates the effect, the true quantum Hamiltonian describing the spins of the phonons.
But what does it mean quantitatively incorrect? I mean, quantitatively, we have no chance either classically or quantum mechanically to ab initio describe nature, I guess.
So I think some people believe that we do.
Okay.
I mean, critical exponents, maybe.
Yeah, critical exponents are qualitative
Yes, right,
things
right.
that we can probably use Langevin equations and classical field theories in finite temperature to
They
describe.
may or may not be true.
But I think what Sam is saying is that it is true.
What I'm interested in here is actually the non-universal stuff.
Yeah.
Yeah. So in a sense, I'll describe in more detail through the talk. So what I want to know is basically if I see some relaxation of the spins in time, what does that teach me about entanglement in the thermal state? Okay, and I don't want to spoil the ending, so we'll see exactly what it teaches us soon, and then you will be satisfied that it is non-universal. Okay, so the next point, of course, is that it's not just that the dynamics is really driven by some complicated quantum Hamiltonian. It's also that the equilibrium states don't really look like classical spin configurations, right? So of course, we can write down any mixed state of a quantum system as some statistical ensemble of pure states. And what I want to imagine is that these pure states are dressed classical spin configurations, okay? So we should imagine that we have some kind of input here, which is some, all zeros in this case, some product state. And then the pure states in our ensemble are kind of dressed. So this is a unitary circuit that describes the dressing of some classical configuration. And so what I'm interested in here is, and this is going to be the key quantity that measures the kind of amount of quantumness in the thermal state, is the minimum allowed depth of this ensemble of circuits that describes my thermal state, okay? So what we'll see actually is that at low temperatures, when you want to describe your thermal state as an ensemble of pure states, you cannot get away with describing it as an ensemble of product states. It's going to be an ensemble of these kind of dressed, quantum fluctuating, not quite spin configurations. And so this minimum depth vanishes at high temperatures, we now know, following this result I mentioned earlier from the computer science community. What we'll see is that as you pass below some order 1 temperature, this circuit depth starts to increase and in general becomes some function of beta. What I want to really highlight is that this depth here, it's really a measure of the complexity of the thermal state that mods out all of the classical correlations. So what I mean by that is that if we took, for example, some classical spin glass, where there's some correlations between the spins, but these correlations are extremely complicated at low temperatures, the depth for that classical spin glass is still going to be 0, right? So we're just seeing the amount of dressing on top of the classically correlated background.
Excuse me, at high temperatures, should I think of the depth as really being 0, or should I think of it as being order 1?
So in my definition, if I just have single qubit rotations on each of these sites, that's depth 0.
But okay, so it really is 0 in that.
It really is 0. So it's really surprising. So the point is that at high temperatures, these thermal states, they are statistical ensembles of product states, but in various bases, right? So it's not that all the spins are in the Z bases, some are in X, some are in Y, but it's a statistical ensemble of totally separate, totally unentangled states. Okay. So the idea is going to be that what I'm going to show you through this talk is that by looking at the dynamics of the system and standard spatial correlations, you can see how much dressing is necessary to describe your thermal state. And so you can see kind of how far away you are from some effective classical description. Okay, I've sort of already said this. So at 0 temperature, many of us are familiar with the idea that the entanglement in a quantum state is associated with spatial correlations. At non-zero temperature, what I'm going to show you is that entanglement is related not just to spatial correlations, but to differences between those and temporal correlations. Like, so how the system relaxes in time is going to teach us how dressed these thermal states are. Okay, so let's have a little bit of a review to see what's going on here and to understand why it's a little bit challenging to relate the things that we observe to the entanglement in mixed states. So let's start with the easy case of a pure state. Imagine we have a bunch of spins in some superposition of a bunch of different configurations. So in this setting, if I now imagine I compute some spatial correlation function between two local observables, here called OA and OB, then if the connected correlation function is non-zero, then that means my state cannot be a product state, okay? The existence of any spatial correlations, any connected correlation, implies there has to be some entanglement in your pure state. So, of course, this is not going to work. This statement is not going to hold for mixed states. But what I'm going to try to do is generalize a statement of this kind to thermal states. The reason it's challenging to do that is because in a mixed state, there can be correlations even when there's no entanglement, right? So imagine I just had some classical ensemble of spin configurations. So now I'd say that, you know, my state is this configuration or this one or this one. There's no coherence. Then, of course, I can have arbitrarily long-range correlations between local observables, even though there's no entanglement. So to understand the connection between correlations and entanglement, it's going to be useful to think about this slightly abstract concept called monogamy of entanglement. For those of you who are not familiar with this, so monogamy is a kind of exclusive relationship between two entities. So for temperatures lower than something of order unity, we do know that thermal states are generically entangled already. So the question here is, the question that I want to address is how the entanglement that we know is there in thermal states is encoded in 2-point correlations, let's say. So to see, or to get us towards the answer, we're going to first off consider something that does not work. So we imagine we have some thermal state. We are interested in at some arbitrary temperature. And what I want to ask is, well, is the fact that this thermal state is entangled encoded in the reduced density matrix of A and B, okay? So the reduced density matrix of A and B captures all of the spatial correlations between A and B. So if there was some connection between these spatial correlations and entanglement, it had better be in that object, right? But that's, it turns out actually that rho AB is not entangled at all in many of the situations we care about. Even if we go all the way to a ground state of this highly entangled quantum spin chains, this is the spin 1/2 antiferromagnetic Heisenberg model. So, you know, the ground state of this thing is sort of as entangled as they come. And there are power law correlations between the spins that we usually associate with the entanglement in the ground state. So the thing is that although we have these power law correlations that we associate with the entanglement in the ground state, rho AB is actually totally separable beyond nearest neighbors in this case, okay? So although there is entanglement, that is not something that appears in the reduced density matrix of AB. So the reason for this is pretty simple. So the reason is that in a locally interacting many-body quantum system, nearby degrees of freedom are more entangled with each other than they are with faraway degrees of freedom, okay? So A and B, they're just more entangled with what's going on around them in C than they are with each other. So they cannot be entangled with each other due to monogamy. Okay, any questions here?
That's good. When you say the thermal state is generally entangled, do you mean the neighboring part are entangled or separate part?
I mean, if we take the whole many-body state and we try and chop it in half, then there's entanglement across a bipartition.
This means greater than 0.
I mean that it is non-separable, yeah. But there's gonna be something more quantitative that appears soon. But yeah, so that just to be clear, this is the question. The question is how you see from local correlations of faraway observables that the whole many-body state has some bipartite entanglement through it. Okay, we're going to think about a little thought experiment here, and ultimately this is going to lead us to some ideas from quantum key distillation. So what we're going to think about here is just kind of measuring an observable. So we take our many-body system, and we imagine that we take this measuring device, which is this blue spin, and this measuring device is going to be used to weakly measure, or just measure actually, some observable OA. The weakness of the measurement will be important later. For now, we consider some arbitrary measurement of this OA that involves coupling this spin to it and then measuring the spin. When we do the measurement, we find that the spin is either pointing up or pointing down. This is our binary measurement outcome. And then when we perform the measurement and we kind of keep track of the outcome, then we get some post-measurement state called rho m of the whole system ABC. So a very important point here is that when you perform the measurement of OA, you can change the entropies of different parts of the system. You can learn, which just means you learn something about them. So after I've done the measurement, it might be that when I've measured, I've measured A, I've kept track of the outcome. My measurement can do something non-local, and in particular, my measurement can reduce the entropy of subregion B. It can also reduce the entropy of subregion ABC. And this delta SB is just the average entropy change over measurement outcomes when you perform this measurement in A. Okay, so the really important point is that the effect of the measurement is going to change in a very important way with temperature. So let's start off thinking about zero temperature. Okay, so at zero temperature, our states are pure. When our states are pure and we perform these measurements, they go from being pure to pure. So the change in the entropy of the whole system ABC is 0. On the other hand, when we do the measurement in A, because there are correlations generically, we will find that the entropy of B is reduced. Okay, go to infinite temperature and things are flipped around. At infinite temperature, if you do a measurement of A, the entropy of the whole state ABC will be reduced, but there are no correlations, so the entropy of B is not changed at all. So remarkably, it turns out that actually this very simple criterion tells you whether the state of ABC is entangled. Much later in this talk, towards the end, I'll relate this to standard correlation functions. For now, this is a very generic statement about changes in entropies induced by measurement. If you can do a measurement of a subsystem in a many-body system, and you find that your measurement reduces the entropy of another subsystem by more than it reduces the entropy of the whole state, then you have to be entangled. There's no way around it. Okay, so this idea looks like it comes out of nowhere. Really, this is the criterion, this is the condition that would allow a party A to perform one-way quantum key distillation from A to B, where the environment that purifies the whole system is a kind of eavesdropper. So I'll talk a bit more about that on the next slide. Any other questions about this point?
Does this speak at all to the nature of the classical mixture at different temperatures? So I have two different temperatures that are both a classical mixture. Are they decomposed necessarily in the same set of product states?
So you're imagining you're in the high temperature regime.
High temperature regime where we have classical mixture of product states.
Mm-hmm.
Is that set of product states independent of temperature?
No. So, I mean, the probabilities of the different product states will change with
The
temperature.
probabilities will change. Will the product states themselves?
I would think that generically, without fine-tuning, I'd think that every product state appears with some probability in the high temperature regime. Unless there's some symmetry that forbids that.
In some basis or literally all?
Yeah, all possible. Okay, so the way, right, sorry, I should clarify. So in this high temperature regime, let's stick to qubits where more is known. So in the qubit case, you have a pure state that is a statistical mix, sorry, your thermal state is a statistical mixture of product states where the spins are in either the Z, X, or Y basis. Okay, so you can get away with a discrete basis. And so there's 3 to the n different product states. And in general, all of them will have some non-zero probability, and those probabilities will vary with temperature. But throughout that whole regime, the key thing is you're not going to be able to satisfy this criterion because the state is separable. Sure. Okay. So is that 10 minutes to questions or 10 minutes total?
10 minutes, so yeah, question.
Okay, great, thanks. Okay, so let me just talk briefly about how this is connected to QKD. And so this is also going to come back to this kind of monogamy idea. So what we should imagine here is that we have ABC, which is our system, and E here is this other entity that purifies ABC, okay? So ABCE, that's a pure state. So the environment knows kind of everything there is to know about the system, given the energy of the system in this case, given the energy expectation value. And so let's go back to our kind of measurement protocol. So we imagine that Alice comes along and measures some observable in subsystem A and gets some outcome that's plus or minus. And then on doing this, Bob, in principle, receives some post-measurement state of their subsystem. It's updated because it was correlated with A. And Eve gets similar. Eve's state is updated by the measurement in A. And so the point is that there is a protocol, which I won't have time to describe, where Alice announces some judiciously chosen information about their string of measurement outcomes after repeating this whole thing many, many times. You do this many times, Bob ends up with a tensor product of these row Bs for different runs. Alice has some classical bit string. Alice judiciously announces some information about that bit string. And on announcing this, Bob is able to decode from their many copies of the state a number of bits of mutual information that is controlled by the entropy change of B. Okay, so
how do we have many copies? Because it's done many.
Yeah.
Experiment is done many times.
Exactly. So you reset, everything gets reset, and you repeat the whole experiment many times. So Bob has this tensor product of lots of row Bs, and then the idea is that Alice announces some property of their bit string. Bob then performs a measurement on their many copies of the density matrix, and then is able to decode n delta SB bits of mutual information with Alice's bit string. On the other hand, Eve is able to decode n times delta SE. Okay, so there's some kind of code book that's known to everybody for this procedure, but I won't talk about. So the basic idea here is that if when Alice does this measurement, more information is revealed to B than to E, and crucially the change in the entropy of E is equal to the change in the entropy of ABC, then Bob sort of gets more information than Eve. Okay, and because Bob gets more information than Eve, that means there is a way of processing your classical bits so that Alice and Bob share perfectly correlated classical bit strings that Eve is not in on. Eve is hidden from Eve. And this is what I call a private classical correlation. Okay, so the notion of privacy I'm talking about here is one where A and B share some information that E is kind of cut out of. But crucially, and this is why this concept is so useful in many body systems, C can know what's going on in A and B. Okay, so these ideas from quantum key distillation allow me to define a notion of privacy where A and B can have some correlations, and I can kind of choose who's kind of excluded. Okay, but if I was talking about entanglement, I wouldn't have that freedom. Okay. So I think that's the last thing I'll say about QKD. So if that didn't make any sense, don't worry about it. Okay, so the next thing I want to say is that the entropy inequality I've just described really provides us some pretty direct insights into how dressed these equilibrium states are. So let's go back to our expression earlier. So we imagine we have some thermal state that's some kind of quantum fluctuation, some unitary circuits acting on some product states. And what I want to know is how deep these circuits have to be. That's this depth D. And so what we should imagine now is that we have our many-body system. There was some measurement that could have been performed in A that reduced the entropy of B by more than it reduced the entropy of the whole system ABC. And if you find that this inequality is satisfied at beyond a distance x, then it must be the case that the depth of the circuits is larger than x over 2. It's kind of a light cone bound. Okay. So the point is that if you can do this measurement in A that reduces the entropy of B by more than it reduces the entropy of ABC, then the past light cones of A and B have to intersect each other. There's another way of thinking about this where you bring in the eavesdropper, which is just to say that if without thinking about any measurement, first off, if you take your many-body system and you find that the mutual information between two parts of the system is greater than the mutual information between one of the parts of the system and the environment, then the circuit depth has to be greater than x over 2. Okay, so this allows you to see how dressed the state is. Okay, so let me just give you a quick example because this is getting pretty abstract. So let's suppose we were thinking about a thermal state of the transverse field Ising chain, and we imagine that we take some, A is going to be a single site here where I'm going to measure the x operator. B is going to be like a semi-infinite part of the system that is separated from A by x. Okay. So I take these thermal states and I can just start computing these lower bounds on the circuit depth. And you might guess from the fact that sorry, I'm at the critical point, sorry, at G equals 1. You might guess from the fact that you have conformal invariance at G equals 1 that the circuit depth is going to go like 1 over temperature. And this is exactly what you find. So you find that if you take thermal states of the transverse field Ising chain at temperature T, then as you lower the temperature, those thermal states, so say at the critical point, which is in blue, as you lower the temperature, the ensemble of pure states that is the thermal state has to have a depth that is at least 1 over the temperature with some prefactor.
And is this tight or?
It's almost certainly not tight. So it's just a lower bound. But yeah, thanks for that question. Any other questions about this result? Okay, so now I'm going to tell you, I'm going to finally bring it back and talk about what any of this has to do with local observables. So the key point is that if you is that if you think about a weak measurement, you get this very simple relationship between this inequality and an inequality between regular old spatial correlations and temporal correlations. So if we do this weak measurement, which essentially corresponds to A, weakly coupling a measuring device to A, and then weakly coupling a measuring device to A, and then measuring their measuring device, and then you imagine that B measures some observable OB, you can see that the change in the entropy of B is lower bounded by just this regular spatial correlation function, okay? Mu is the measurement strength, don't worry too much about it because it's going to drop out. So the one side of our inequality is lower bounded by this regular spatial correlation. And the really surprising thing actually is that if you take a thermal state and you weakly measure an observable, then the amount by which you reduce the entropy of the whole state is actually related to how quickly the observable would have relaxed in time under real-time dynamics, okay? So I want to clarify that actually there's no dynamics in the problem to begin with. I'm just taking a thermal state, I'm measuring an observable, and I want to know how much did that measurement reduce the entropy of the whole system. It turns out that that reduction is related to how quickly the observable relaxes in real time, okay? So f is some function that we know that is kind of horrible, but it exists. So
is there some relation to kind of thermodynamic relation, or thermodynamic entropy production? Because this is like production of entropy in the whole system.
yeah, it'd be nice to develop something like that. But yeah, for now I don't know if there is a connection to that. But yeah, it seems like there should be, right?
Yeah, because it's a dissipative process.
Yeah, right. So so here, yeah, right. We can talk about this a bit more later because I don't have anything more to say about that. Any other questions here?
Loosely, what's the direction it goes in? Like the faster it dissipates, is it that the entropy decreases larger?
Yes, right. So if you measure an observable that relaxes slowly in time, then this means you get a large change in the entropy. So a simple example, let's imagine that you had a thermal state of a magnet in its ordered phase, right? And so, you know, the thermal state is a statistical mixture of the spins are mostly up or the spins are mostly down. So if I measure the order parameter, z, this is an extremely slowly relaxing observable. And on measuring the order parameter, I reveal a bit of information to the environment. I measure whether my spins are up, and this kind of magnetizes the whole universe. And so in that case, I get a large change in the entropy. Okay, so something that I find extremely interesting about all of this is actually that when you get lower bounds on circuit depth from this, you just want to compare this temporal correlation function with this spatial correlation up at the top. This comparison gives you a lower bound on the circuit depth, but actually constructing that lower bound doesn't require you to know the Hamiltonian. It only requires that you can see how quickly the observable relaxes in time. So so earlier on I was talking about this idea of like just looking out at materials and asking, given how I see them, you know, given the behavior I just see in few body correlation functions, how can I see that entanglement is important in that description? I can see that entanglement is important in the description just through the comparison between the two objects shown here. Okay, in that way I can see how much quantum dressing there is in physical systems. Okay, so that brings me to the Also, I should also flag that there are connections between this and the quantity known as the quantum Fisher information. So the quantum Fisher information allows you to see multipartite entanglement in many-body systems, also without knowledge of the Hamiltonian, and by looking at response functions. So there, the idea is you think about a kind of fictitious metrology problem where you use your quantum material as a quantum sensor, and if you find that, and it turns out its quality, its ability to quantum sense is encoded in two-point functions. So here we're considering a similarly strange task where we ask if we can use our quantum material as a kind of resource for quantum key distillation. I'm not actually advocating you do that, but the point is in both of these cases, you have some quantum information task that provides you with some relation between physical properties and entanglement. So this brings me to the end. I've talked about how the dynamics we observe in experiments can reveal how dressed equilibrium states are. So in order to arrive at these relations, I use some concepts from quantum key distillation, which is, just to reiterate, it's very powerful in this setting because it allows you to define a notion of privacy that's quite natural in many body systems. And something I didn't talk about here, but I can talk about a bit later, is that what you might think of as equivalent ensembles, say canonical ensembles and grand canonical ensembles, can actually have very different entanglement structures. So, okay, obviously there's kind of a long history over the last few decades of trying to connect the entanglement of quantum ground states to the complexity of describing them on computers, and also to the correlations in those states, and the way that you get the relaxation of zero temperature correlation functions. So this is a very nice web of relations, and what I'm talking about today is kind of a step towards developing a similar web of relations for thermal states. So yeah, thank you all for listening. Brian?
So you've been talking about this metric of circuit depth and sort of morally saying, oh, it's sort of measuring the entanglement. But most states require much larger circuit depths than are required to build up the necessary entanglement. Do you have a sense here for the metric, the metric that you're using? Is it really measuring sort of the depth to get the entanglement in that state, or is it measuring this sort of slightly more subtle thing of actually how much circuit depth you need to build up these individual states that are in a statistical mixture?
Yeah, right. So so there's this separate problem of actually preparing the state, right? You can imagine Monte Carlo sampling a circuit and then building evolving the system under the circuit.
Most states require much deeper circuits that are needed to just build up the entanglement.
Absolutely, right. So in this case, this is why I was grounding everything in regular correlations. So the question is just, given the correlations that I observe, what circuit depth is necessary for that? It could be that if you actually wanted to prepare the state, a much deeper circuit would be required.
This is essentially,
I think because we're a little bit behind, that we should, take one more question and then.
Yeah, okay.
So in this relation between the quantum Fisher information and multipartite entanglement, there is a hidden assumption that the spin degrees of freedom are all the degrees of freedom, and there is no coupling to the phonons, which I guess is okay in neutron scattering experiments if you look at sufficiently high frequency. But I think your statement is stronger than that, that basically it doesn't matter here whether you're coupled to phonons or not, and the entanglement is.
So in our case, it doesn't actually matter if you're coupled to phonons or not. But I think I've been thinking about this a lot over the last day, and I think that the quantum Fisher information is also not sensitive to this. So, but yeah, let's talk about it more later.
I think they need that observable that they look at is just a sum of all the degrees of freedom.
That's actually so in all of the published papers on the quantum Fisher information, that restriction is there, but I also don't think that's necessary. So I think you can go a bit further with what's currently in the literature. But yeah, here I don't require that the spins are all the degrees of freedom.
Where my CLI is running, and then I can render the markdown files and open them.
And just as we wait for people to come in, I want to point out, as you're leaving, there is a basket to drop here, unless you want to keep the neodymium magnets. Sticking stuff to your fridge, but otherwise, please return them. Great. So we're gonna start our last session with Charles Stahl, who's going to tell us about his Brownian Ratchets.
Yes. I think the microphone is working.
Charles is at Stanford.
Thank you all for staying till the last day, and thank you to the organizers for inviting me. I grew up in Wisconsin, so being here in Minnesota feels almost like being at home. So it's been really nice. Yeah, the conference has been really good. It's been fun to see Minneapolis. I'm going to tell you about a project that I've been working on that will appear on the archive soon. This is work with Vedika at Stanford and Ethan at Berkeley. And the way that I will tell the story is I'll start with sort of some introduction on non-equilibrium dynamics and both microscopic perspectives and macroscopic perspectives on these things. And then I'll tell you about some sort of interesting examples, illustrative examples, and then I'll tell you about our result, which is how to simulate generic cellular automata using just like simple driven systems. So the talk will be entirely classical, but I will tell you about what this means for quantum dynamics at various points throughout the talk. So active dynamics are everywhere in our world. A nice, pretty picture to show when talking about this is bird flocks. They form these really cool shapes. But from a more statistical physics perspective, the reason that they're interesting is because there's this model of birds flocking in 2 dimensions that's able to break a continuous rotation symmetry, even though that's not allowed in equilibrium. So the point is that they're able to do things that equilibrium dynamics are not able to do. Inside our bodies, there's these things called kinesin molecules that can just use coupled to a potential difference between the inside and the outside of a tube, and use that to have directed motion along these tubes. This is like going on inside your cells. And then a more like lattice perspective is a thing called cellular automata, which are just sort of systems of bits that interact with each other locally, but can have these really impressive emergent phenomena. And what these all, the way that these are usually described is in terms of the dynamics of the microscopic degrees of freedom. So in this model of bird flocking, this is called the Fixet equations. And they say that you look at each individual bird and then update it based on its surrounding environment. Or similarly, for these cellular automata, the way they're usually framed is that you take each individual bit and look at the bits around it and then decide how to update the bit. But this is very different from how we usually talk about non-equilibrium systems in condensed matter physics. So in condensed matter physics, we usually have some material and then we drive it out of equilibrium, but we do it in some sort of macroscopic way. So maybe we have a time-dependent Hamiltonian, maybe a coupling to some cold bath to keep it from heating up too much. Maybe in some sort of like classical Hall type setup, you have a high voltage side and a low voltage side, and that drives currents from high to low voltage, but maybe it also drives some transverse currents. And these macroscopic perspectives on non-equilibrium systems are useful because they allow us to talk about the system when it's closer to equilibrium. There's fewer degrees of freedom to keep track of, and maybe it's easier to generalize. Maybe you can talk about some RG or something like that. So on its face, maybe these 2 paradigms look very different. You have something that's very interactive, lots of degrees of freedom that you have to keep track of, compared to something that's more autonomous. Like you only have to keep track of maybe a single degree of freedom, like the time or the potential difference between the 2 layers. And what I'm going to talk about today is how to use memory experiments to put them on equal footing so we can really compare them to each other fairly. The paradigmatic example is the Ising model. So you have let's say you have some magnetic hard drive, which has little magnetic domains in it, and you want these magnetic domains to maintain their magnetization. So you put them in your cold fridge. And then you can model this with Glauber dynamics. So every spin looks at the 4 spins around it and just tries to match them with some probability based on the temperature. And these dynamics have a phase transition. As long as you're below the critical temperature, if you start with a mostly white system or mostly black system, it'll maintain its magnetization for an amount of time that scales in system size. But if you turn on a field that prefers one of the states, these systems very quickly evolve to look like each other. So you forget the memory. The memory time is finite. It diverges as you make the temperature very small, but it doesn't diverge with system size. So you can like watch the system melt away, watch the memory melt away. And this is actually a problem in real world materials. Like if you take your hard drive and let it sit for too long, the stray magnetic fields can corrupt the memory. So like you have these different domains that are next to each other, and one of them can affect the other. This means that if you're doing some sort of like long-term storage, you have to go back and make sure it's okay every once in a while. But an alternative to this is what's called is active error correction. So a particularly illustrative example of active error correction, and one that I think is really easy to compare to Glauber dynamics for the Ising model, is this thing called Thom's rule. And the idea is that every spin still tries to match its neighbors, but it only tries to match its north and east neighbor. So this seems like a very mild change, but it means that you can't think of this as the Glauber dynamics of any local Hamiltonian. And that's basically just because it's non-reciprocal. So one spin, the north spin affects the center spin, but the center spin has no effect back on the north spin. So that means that you have to have some sort of agent looking at the system and making these changes. But you can still talk about a phase diagram where now this thing that I'm calling temperature is now a noise parameter instead. But you can still see that if you park yourself below the phase transition, you'll have two systems that will remember their magnetization. And then you can also see, as you look at this, you can see that there's sort of some directed motion towards the southwest, and that's because of this northeast rule. So things get pushed in a particular direction. And the reason that this is really cool is that you can even now turn on something that's like a magnetic field. It's just now just a bias in the noise, but you can think of it as a magnetic field, and the memory remains stable. So it's hard to see in this picture because the memory remains stable. It's hard to see that they're different, but maybe if you look closely, you can see that the domains on this side are much bigger. So there's some noise in the model that's favoring white, so it's making bigger domains on this side, smaller domains on this side. Nevertheless, for an amount of time that's exponential in the system size, you'll still be able to remember your initial magnetization. Yes?
Find those patterns moving in same direction?
Yeah. So the reason that they're all moving from the northeast towards the southwest is because of the way the rule is constructed. So every spin updates based on the state of its north and east neighbor. So that means that the influence sort of only goes in one direction. So if a small island forms, then it gets pushed in that direction by the dynamics. Yeah.
Oh, what would happen if you switched over to a hexagonal grid rather than a square grid?
As long as you make sure that the update rule breaks inversion symmetry, you'll maintain this this nice scaling even with bias. So this is a little bit different from how we think about active dynamics, usually in error correction, in quantum error correction. So obviously, active dynamics are super important in quantum error correction. But usually what people talk about is some sort of active global dynamics. So you take the stabilizer of your entire system, the syndrome of your entire system, you have to process all of that information at the same time, maybe do some computation based on that syndrome, and then feed that back to the system. So this is a very global picture. You have to look at everything all at the same time. But there is recent progress towards local decoders, including some work from Fiona. So I'd like to think of this as both motivating this talk is like why we care about local decoders. Why are they better than the global decoders? So now just to review this comparison, we have on the one side, we have the sort of self-correction, which is thermal dynamics, just some system sitting in a fridge. The other end of the spectrum is the global correction that you have to do for the toric code or the surface code. And these local dynamics sort of sit in between the two. So they're local, which makes them look a little bit more like thermal dynamics, but they're active. There's someone doing something that makes them look a little bit more like this system for the toric code. And that'll be the thing that I'm talking about today. And the things that make these local dynamics interesting and different from thermal dynamics, you can think of it in a few different ways. On the one hand, they're non-reciprocal. Like I said, for Thom's rule, different spins will have effects on their neighbors that are not the same as the effect that the neighbor has back on the individual. They'll carry currents in the steady state. So this is something that's forbidden in equilibrium, but is very common in these active systems. So what that means is that something is doing work. And then this is a common perspective to take on active dynamics. But what I want to really push on today is how we can see the work being done on the system. So if we can just take our system and say, I'm doing external work on the system through this process. And then these always allow you, these can allow you to accomplish some task that's impossible in equilibrium. But what I'm going to eventually get to is an equivalence between what I was calling local active dynamics before, and then these sort of simple driven systems. So there's what I'm gonna call a Brownian pump, where you have some driving and some dissipation, and that's the only source of activity in the system. And then something inspired by this classical Hall system, where now I have a hot side of the system and a cold side of the system. That means that heat will be flowing through the system, and then that's enough to generate your active dynamics as well. There's a little asterisk here that just corresponds to the synchronicity of the dynamics. Like sometimes when people talk about local active dynamics, they also require that there's some global clock that's synchronized across the whole system. You can think of that as like the synchronicity in the drive. So you can't get that in this system, but up to that, these are all 3 equivalent systems. So the pumps, I'm just going to flash through, and I'll spend more time. The rest of the talk I'll spend on the ratchets. But the pumps, our result is that you can come up with some Hamiltonian with the function of time, and it will simulate your cellular automaton sort of arbitrarily well in some particular limit. So you sort of turn your Hamiltonian parameters very large, turn your temperatures very small, and you'll get arbitrarily close to the cellular automaton. And this is related to some previous work. And maybe that seems less surprising because like often people talk about active dynamics with driven systems. But what I think is a more fun illustration, and then I'll have lots of pretty pictures to show you too, is how you can turn this into something that just depends on a temperature difference. So like way back in the 1800s, people doing physics were really wanted to figure out how to get motion out of just temperature differences. Like this is what a steam engine does. And if you've ever played with Stirling engine, this is something maybe you've played with in like an introphysics class. If you've never used one, you should like find your local lab manager and see if they have one that you can just play with. But you can actually have some that just are driven by the temperature difference between body temperature and room temperature. So you can hold this thing in your hand and it'll just start to spin. So I think that's pretty fun. And then this Brownian ratchet that I'll actually go into depth explaining what it is. It's sort of a very abstracted version of this. So let's actually, I've said this word a bunch of times, let me tell you what it actually is now. So you imagine that you have 2 sides of your system. You have a hot side and a cold side. On the hot side, you have some paddles. They're in a box with some hot air. The air is hot. That means that there's some Brownian motion. The air molecules are going to hit the paddles and make the paddles sort of wobble back and forth. But now the paddles are connected by a shaft to a ratchet. It consists of a gear, and then this blue thing is called a pawl. So the pawl allows the ratchet to move in one direction, but not the other. So what that means is that as these paddles try to wobble back and forth, they can move this way, but they can't move back because of the pawl holding it in place. So this is a way to extract useful work out of a temperature difference. But let's turn this into a lattice model to make it, like amenable to our purposes. Say you have 2 particles hopping on a line, and I'm going to call them the leader and the follower. The leader is like the hot gear, and the follower is like the cold pawl. The temperature, the Hamiltonian is going to be 0 if they're sitting on the same site. So these are the ground state of the system. There's going to be some small energy associated with the leader being just 1 step ahead, and then some large energy associated with other states. So the follower is going to be at some temperature that's much less than this energy difference. So the follower, let me see. Yes. So the follower will always want to hop forward to match the leader. But the leader is now much hotter than the energy difference. So it means that the leader can sort of wobble back and forth, and then the follower will always catch up. So you can actually see this happening. The leader is wobbling back and forth, but then anytime you update the follower and the follower is behind, it jumps forward to catch up. So you can think of, there's like a very close analogy to the classical Hall effect, where you have a high potential and a low potential. This generates an electric field, and then the electric field pushes a current in the transverse direction. What's going on in this Brownian ratchet is instead of a potential difference, you have a temperature difference. So this generates a gradient in the temperature, and then that generates the current moving in this other direction. So let me just show you the video again because it looks fun. Any questions about that so far? Yeah.
Is this Hamiltonian or like that H? Like
Yeah, it's a few body Hamiltonian. So like think of the blue dot is this XF and the red dot is XL.
oh, okay, but it's not included because follower and the leader use a different temperature.
And this is Hermitian.
The Hamiltonian is Hermitian. The Hamiltonian, it's a classical Hamiltonian, so it's like it's maybe the word to use is reciprocal. The Hamiltonian is reciprocal, but the reason that you get this directed motion is because of the temperature difference between the two. So you can mimic non-reciprocal effects using a reciprocal Hamiltonian and a temperature difference, a source of energy. So this example was few body, so let's move on to a many body system because we like many body systems. So the many body system is a little bit more complicated, but I'll walk you through the different ingredients. Our goal is going to be, I guess I should have said this, our goal is going to be to simulate dynamics that look like this Thom's rule. So we're going to have a square lattice. We're going to actually have two square lattices stacked on top of each other. One of them is going to be hot and one of them is going to be cold. So that means that there will be some heat current flowing from the hot one to the cold one. And then the Hamiltonian just has a few parts. The first part here is like that first term in the few body ratchet. It makes the follower spins just want to match the leader spins. Now these are Ising variables now. Ising spins. And then the second term is going to be a term that for every leader spin, it makes it want to match its followers in the north and east directions. So I've drawn it here with a solid line for J, which is the large interaction, and then dashed lines for K, which is the small interaction. And it's the same deal as before, because the follower is very cold, it will always want to update to match the leader. But then because the leader is hotter than this energy difference epsilon, it's perfectly happy either to match its follower or to match its north and east neighbor. So let's see how this can simulate the Thom updates. We'll start in a configuration where Thom's rule would tell this central spin to update. So our goal is eventually to get the central spin filled in. I'm using like filled and empty as spin up and spin down. So currently this spin does not match its north and east neighbor, so we'll want to update it. But it does match its center. So this one on its own won't update. But we can look at the thermal updates of the leader spin. And now with the energy scale J, it's coupled to this one. With energy scale K, it's coupled to these two. So it'll sort of wobble back and forth, just like the leader in the few body case. So it's going to maybe step forward to match the north and east, then maybe step back. So it's going to wobble back and forth a few times. But then eventually, at some point when it's in this state where it's matching the north and east neighbor, you'll try to update the follower. And remember that this one is much colder than this energy difference epsilon, so it always wants to match the leader. So it does so. And now we've effectively done the update that we wanted to do from Thom's rule. So now you can simulate the system and see all of these different things happening. So if the two temperatures are the same, the leader and the follower, it's just like an equilibrium Ising model. So at h equals 0, it can remember some information, but if h is non-zero, it'll eventually fail and melt away. But if there is a temperature difference, you can see these same patterns that we saw in Thom's rule. You can see the domains moving from northeast to southwest. And even if you turn on field, you can still see that the domains get a little bit bigger, but they still don't grow too big. You can look at the phase diagram for this thing. So what I've done here is I've set j equal 1, k equal to 0.8, and then on the left, I'm looking at h equals 0, just looking at the magnetization squared, so just the order parameter. So there's some like bulge in the middle at low temperatures, T leader on this side and T follower on this side, where if they're both cold enough, the system orders. If either one gets too hot, the system doesn't order. But then you can extract the critical H. So of course, if the system doesn't order, the critical H field is 0. You also know that on this diagonal line is equilibrium, where the two temperatures are the same. So the critical field better be 0 on this line. It's not exactly 0, but this is just some finite size effects. But once you go very far off of the diagonal, you can see that there's some critical H field, and it's of comparable scale to the other, like the temperatures and energy scales in the problem. Any questions about that?
Sorry, I missed what M here?
M is the magnetization. So this is like you sample from not equilibrium, but sample from the steady state and say how magnetized is the system. So this blue region is where the system maintains some magnetization, and the white on the outside is where the system just relaxes to 0 magnetization. So this is morally equilibrium because H is 0, and this is the one where you can really see that it's doing something non-equilibrium. Oh, and this star is just that on the axis, because it's an Ising model, you can exactly calculate the critical temperature. So the star is just saying that my numerics aren't totally meaningless. So that was just I think a particularly illustrative example, but we can also talk about generic cellular automata. So the way that cellular automata are built is that you just have an update rule. So you look at a spin, you look at the 4 neighbors, and then you update based on the state of the neighbors. It doesn't have to be a majority vote, and you can actually get cellular automata that are very interesting, that are not just majority vote cellular automata. So this is the game of life. You have these emergent ballistic particles that move, and you can even, they're called gliders. You can have these systems that spit gliders out continuously. And I mentioned before this difference between synchronous and asynchronous. So this is like in the game of life, people talk about synchronous updates where you have to update all of the spins at the same time. And what I was showing you before with the ratchet was very asynchronous, like each of the spins just updating on its own individual clock. And generically, cellular automata have no error correction properties. So if we're simulating them with a thermal system will have some errors. And if the cellular automaton can't tolerate any errors, the simulation isn't very useful. So like the reason I was focusing on Tome's rule is because it has these error correction properties, but I think it's still worth talking about generic cellular automata. So we have a similar construction where the first term is like the first term from before. It just wants the 2 spins to match. The second term is that the leader wants to match the cellular automaton updated state of the followers. And then similarly, you have like some energy scales. The follower temperature is much less than epsilon. The leader temperature is much greater than epsilon, but smaller than J. This last term is, I don't know, maybe just a technical term. You have to cancel out some like back reaction from this term. But once you've constructed this thing, you can actually prove some things. That the dynamics that you get from this Hamiltonian, as long as you work in this limit where one of the temperatures is greater than the other, the dynamics that you get will simulate your chosen cellular automaton arbitrarily well. So I'll just move on to some outlook, and then I'll have some time for questions. Remember that in the bird flocking analogy, the way that the energy is getting pumped into the system is somehow because the birds move ballistically in a chosen direction. So this is an energy source, just like for what we've been talking about so far, the temperature difference has been the energy source. So maybe we can use other energy sources to get Tome-like dynamics. And in fact, it seems to be the case. If you take some like multi-layer Ising model and just slide the layers in different directions, you'll get similar sort of erosion properties. So imagine that you start with some island like this. Now you slide 3 layers in different directions. You'll get some small magnetization on the parts where where only where the layers are not overlapping. So then if you do a majority vote, you'll remove those regions and slide again, and you'll continue to sort of remove these islands. So it seems like these sliding dynamics will naturally realize something that looks like Thom's rule. And in fact, even in one dimension, you get some not diverging the system size, but some very long lifetimes just using the sliding. So you take a 1D Ising model and just move the two layers in different directions. And it seems like the lifetime is very long. This is in fact a workshop on quantum computing. So eventually we'd want to talk about something that's related to quantum computing. So the way that you would turn this into some dynamics for like a stabilizer model is instead of looking at the states of the individual spins, which of course would immediately destroy any coherence if the spins are qubits, just look at the stabilizers. So like for Thom's rule, you only have to look at the states of the domain walls. And if both of these domain walls are on, you would want to flip your spin. So those types of dynamics where you look at stabilizer states and then based on the stabilizer states apply some updates, this is something that people are thinking about even for local dynamics in quantum systems. So Shankar has some work from last couple of years ago, I guess, and also work from Fiona on these local decoders for quantum codes. And maybe you could even imagine trying to do something more general than this, like some non-commuting Hamiltonian that's a function of time. And then maybe this is my last or second to last slide. Maybe these descriptions would be helpful in thinking about steady state. So there's a lot of work on what is the steady state of Thom. So obviously the state is dynamically not a Gibbs state because it has these currents in it. What if you just look at the static steady state, like you integrate over time? In particular limits, it's known to not be Gibbsian, but still be interesting to try to see that in the entire phase diagram. Maybe you could try to come up with the field theory for these non-equilibrium systems. This would have been a funnier joke about here. And people talk about entropy production, but now that there's actually a source of energy, you can talk about the power efficiency, like how much of the power that you're pumping into the system is actually being useful. In other words, how much energy does it take to protect a qubit or protect a classical bit? Thank you.
What is the when you say steady state, what is the time scale you're considering?
Well, I guess you could look at different timescales. So, like in this video, you can see that there's sort of a characteristic domain wall size, and then that domain wall takes a certain time to transit any particular point. So I think that if you look on timescales that are longer than that time, you would get something that's just static.
Am I right? This timescale doesn't really scale the system size.
That's right. Yeah. So right. So well, there's two timescales. There's like how long does it take to reach the local non-equilibrium steady state, and then how long does it take to reach the global state? And the global state is like the memory time. But that's a time that scales the system size. But you can still look at the local.
That's not your simulation of this cellular automaton has this deviation that just that's given by a separation of scale, which that doesn't depend on system size.
Separation of
scales like temperature and epsilon.
Yeah, that's right.
So you don't have you cannot simulate. Am I right? You cannot simulate the true cellular automaton dynamics up to time scale that is scale with system size.
Well, but you can still say that the time that it takes to reach the true steady state will diverge with system size.
Yeah, really stupid question.
Yeah.
The dynamic that you're doing here.
Yeah.
Is this just the Metropolis Hastings rule, or like, what's?
Oh yeah, right. So it's
more dynamics defined for these classical models.
Yeah, so it's Metropolis Hastings on the individual spins and just with different temperatures. So like Metropolis Hastings with cold temperature here, Metropolis Hastings with the hot temperature here.
Thank you very much.
Like the setup, some of the setup that you presented seems like feasible in real quantum matter. Like, like you also mentioned that some hole allows it to classify. Do you think that this kind of things can be implemented in like real materials?
That would be pretty cool. I mean, I think that you'd have to have two things. You'd have to have a dynamics that are interesting on their own, and then ask whether those dynamics can be implemented in real materials. And I think both of those questions are interesting.
Maybe let me ask. So you mentioned this business of synchronous versus non-synchronous.
Yeah.
So it's on to.
Yeah.
And so it seems to me that anytime you're doing this with a temperature, it's bad, right? This is non-synchronous.
That's right. That's right.
And so is this the sliding dynamics? Is this synchronous?
Oh,
Or is
yeah.
it not at this point clear how to.
It is synchronous because you have to move one entire layer all at the same time. Otherwise, you'll get. I mean, you could think of it in continuous space, and then it could be asynchronous. But if you're thinking about it on a lattice, it has to be synchronous because you have to move an entire layer of the lattice all at the same time.
Yeah, and I guess I'm thinking of Ethan had some examples of cellular automata that were only stable if they were implemented synchronously, including this one that they used to do error correction.
Yeah, right.
And so I guess the kind of broader question is, if somebody hands you that and says, design me a simple process, where I just pick these global quantities, that will emulate that, what is the temperature one is very nice and that's very general. Is there a general approach that solves that problem?
Yeah, so for synchronous, you can do something driven, like with time dependence, because then the time dependence has to be the same everywhere across the system. So that's your clock.
Okay, let's think. Perfect. So we have our very last speaker, Matteo Ippoliti, who is coming from Boston.
Great. Yeah. Thank you so much for having me. Thank you for organizing this amazing workshop. It's been really fun for these 3 days. And thanks all of you for sticking around to the very end. I will try to make it worth your time. So this is a work that fits within the theme of many of the talks in this workshop of learning something new in quantum, something old from quantum information theory and applying it in a new way into many body physics. So in particular, we're going to learn about the clock construction in quantum computing, I'll tell you about, and use it to learn something new about entanglement in ground states of many body systems. This is based on this work in collaboration with David Long at Stanford. Okay, so I will first set the stage briefly about entanglement in many body systems, and then I'll pose the question we address and tell you how we answer. So entanglement, as we know, it's of course it's a resource in quantum information, but it's also a principle for understanding states of matter. So we're thinking about correlations between a spatially local subsystem of an extended many-body system, and these can scale in different ways with the size of that subsystem, and it tells us something about the nature of the many-body state we're looking at. So in particular, in gapped ground states, this entanglement obeys the so-called area law. Okay, so entanglement is mostly short-ranged, mostly shared between neighboring particles. And so if you ask about the total entanglement entropy of this subsystem, it mostly comes from things that live near the boundary. Okay? And maybe there are also subleading corrections that tell you about topological order and things like that. But that's the general expectation here. This can be violated, okay? So you can exceed this area law, for example, in ground states of gapless systems that can describe phase transitions, where, for example, in one dimension, you can get this logarithmic excess entropy beyond the area law, let's say. It also tells about the nature of that phase transition. And then you can have the maximum possible asymptotic scaling of entanglement, which is known as the volume law, in highly excited eigenstates of local Hamiltonians, for example. So in these states, the constituents are very, very entangled over long distances. And so if you look at the entanglement entropy of this subregion, then every particle, even far away in the interior of this region, is long-range entangled with everybody else. So you get this extensive scaling of entanglement. Okay, this is important both for understanding the states of matter and also for potentially simulating them on classical computers, potentially using them as resources for quantum computing. So zooming in on local Hamiltonian ground states in one dimension, they usually obey the area law, as we said. Okay, that means you can picture this as some kind of short-range correlations between the constituents of the system, such that if I cut it in half,
the particles that contribute to the entanglement are mostly in the immediate surroundings of the cut. That's the area law. Or maybe in gapless ground states, you get some longer range correlations and decay in some fashion with distance in a way that adds up, for example, to this logarithmic violation. But one can ask, can we do more? Can we get more entanglement in ground states? And the answer is affirmative. People have constructed in various ways things that are known as rainbow states for kind of obvious reasons, that are basically these ground states that have long-range EPR pairs, okay, so maximally entangled pairs of qubits that are very far away from each other. So that if I cut it in half, I pick up an extensive amount of entanglement from all of these EPR pairs that I'm separating. Okay, so this is not so easy to construct in local Hamiltonians, local transitional invariant Hamiltonians. There are many constructions that have been put forward over the years. My favorite one of the earliest, is this one from Irani in 2009, which is completely insane. It has 21 local states that are enumerated here. So it is a spin 10 system, I guess, with all of these weird states. There are, I think, 9 transition rules in the Hamiltonian and 22 kinetic constraints, something like that. You put all this in, you get some little kind of Turing machine that builds up the rainbow step by step. There's a little worker that creates an APR pair, moves it around, drops it, turns around, makes another one. It's kind of amazing. So it's not easy, but it can be done. And then there have been following constructions over the last decade or so that make this a little bit simpler, okay, with more reasonable kind of local rules and more reasonable Hilbert space dimensions and so on. But nevertheless, this is possible. Okay, local transitional invariant Hamiltonians, you can get this extensive entanglement. However, these states, even though they break the letter of the area law, because they have a lot of entanglement, in some sense, they don't break the spirit of that statement, okay? They are states that are easy to describe classically, okay? You can just draw them. You can make a tensor network of them if you want. And the entanglement is in some sense few body in character. It's mostly EPR pairs, even though they're far apart from each other. It's mostly two body entanglement, or maybe few body in situations where it's not an exact rainbow, but only approximately. And so we can ask, is it possible to have local ground states that have qualitatively more complex structures of entanglement? Okay, not just an extensive amount, but really a kind of complex structure of many body entanglement that is more reminiscent of a highly excited state that is really complex, for example, to describe classically. Okay, is it possible? So we answer this question affirmatively. We construct some concrete models, okay, that are very fine-tuned, okay? So the area law does hold kind of generically, and we have to find very fine-tuned exceptions, but they have the significant advantages of being very simple, very physical. You can write down the terms. They're all small. They're easy to make. So modular is fine-tuning. They're very reasonable Hamiltonians. And the interesting thing is that they're based on an idea from quantum computing, in particular the Feynman-Kitaev clock that I will tell you about in a moment. So this is what we set out to do. Are there any questions on the idea or the goal before I get into it? Okay, if not, let me get into it. So what is this clock construction that I was telling you about? Let me start with the Feynman clock. Okay, Kitaev will come in a moment. So Feynman, as we know, kind of pioneered some of these ideas about quantum computing in the 80s before it was cool. And in particular, he has this very nice kind of popular science article in Optics News, I guess, from '85, where he set out to describe quantum mechanical computers. And for reasons that are a little bit opaque to me right now, people in the 80s didn't want to think about quantum circuits. They wanted to think about static Hamiltonians. Okay? So now it seems a little bit artificial, but he really wanted to write down a static Hamiltonian that can compute. Okay? So he writes it down with a notation that's a little bit hard to parse, but in modern sort of LaTeX notation, this is what it looks like. And it's a Hamiltonian that has two components. Okay, one is a so that your state space has two components. One is a quantum computer with n qubits, and the other is an ancilla that you want to interpret as a clock. So an auxiliary system that keeps track of time, and it has some number, capital T, of states that you can represent, for example, by an electron being at some position T on some chain. Okay, so there are two things that can happen. One is that the electron can hop. Okay, so it can hop from site T to site T+1. It can take a step forward. And as it does that, you apply a gate to your quantum computer. So you advance the computation. Okay, clock advances, computation advances. And then this has to be a Hamiltonian, so it has to be Hermitian. So you have to have the Hermitian conjugate added on top of this, which means the clock is allowed to go backward, and in doing so, it has to undo the computation. Okay? We get these two steps. Clock advances and computes, clock goes backward and uncomputes. This is Hamiltonian. Now, finally, I wanted to think of this as a dynamics problem. So you want to run e to the minus I ht. Okay, you start with your clock at 0 and your quantum computer in a trivial state like all 0. You let this evolve, the clock will advance and will compute. Okay, at some later time, you can measure the clock and you can find some end state of your quantum computation, some probability. So now, enter Kitaev. As always, the date is a little bit unclear because this was kind of private communication for many years and then was written up some years later. But anyway, so he wanted to answer the question of the quantum complexity of the so-called local Hamiltonian problem, okay? Which is to say, basically, how hard is it to establish the energy of the ground state of a local Hamiltonian? And I'm not a complexity theorist. This is not a complexity theory talk, so I'm not going to say much about this. But the idea is basically that this is one of these problems that are in the sort of quantum version of NP. So problems that are easy to verify but hard to solve. Okay. So in particular, if somebody gives you a candidate state for a candidate ground state for your Hamiltonian, you can measure the energy and you can easily say whether or not it has zero energy, let's say, but it may be hard for you to find it. So the way that Kitaev establishes the QMA completeness of this problem is by reducing it from a Hamiltonian problem to a quantum circuit, which then fits within the existing framework for QMA. And the way that he does this is through this circuit to Hamiltonian reduction using precisely Feynman's clock. Okay, so you can write, given the gates that make up the quantum circuit that you want to reduce to, you write down this clock Hamiltonian that contains an initialization term. So you say, if the clock is at the position 0, then you make some trivial Hamiltonian that picks out, for example, the all 0 state of your quantum computer as its unique ground state. And then you have these terms that, as we said, are allowing the clock to advance and apply a gate. Okay. Turns out, if you stay like this for long enough, you can convince yourself that the ground state of this problem is the so-called history state. It's a state that contains, in coherent superposition, the states of the quantum computer at all time steps during this computation. Okay, so this first term over here is selecting the component of this wave function when the clock is at 0. It's saying this needs to be the all 0 state. And then these terms are ensuring that as I advance the clock in here, I have to apply the corresponding gates to this state. Okay, so if I look at overall this wave function, I have the entire history of the computation from the beginning to the end present in that ground state in superposition. Okay, so from this you can do this reduction and establish that this is a quantum mechanically hard problem. Now we take this construction and we want to learn about ground state entanglement from this. So we have to make a few twists to make it relevant to us. The first twist is that we want to make this geometrically local. Okay, so this local Hamiltonian problem was local in the computer science sense. It involved Hamiltonians with few body interactions, but there was no geometry, no lattice, nothing like that. We want to make it actually geometrically local. So we implement our clock as a fermion chain that lives in one dimension and runs parallel to the quantum computer. Okay, so we have spins or qubits that make up a quantum computer that are arranged in one dimension. And we have a tight binding fermionic chain that runs exactly parallel to it. And furthermore, we choose the gate U at time t, let's say, that constituent element of our quantum circuit. We choose it to be a 2-qubit gate that acts exactly on sites t and t plus 1. Okay, so that when the fermion that represents my clock hops from site t to t plus 1, it correspondingly applies this gate to the 2 qubits that are immediately next to it. Okay, so that all the terms that appear in my Hamiltonian now that have this form, if you remember, they act exactly on these 4 side plaquettes in my system. They're perfectly innocuous geometrically local terms. Okay, so this is our first. Oh yes.
Is there a reason you're choosing a fermion?
great question. Not really. We want an exclusion principle. We don't want, for many body physics reasons, we're going to have I'm not going to talk about it. We want many possible clock particles to make a many body system. We don't want them to collide. So fermions give us the exclusion principle. We could do it with hardcore bosons or with spins also. Fermions make it easier to solve analytically using free fermion techniques. But good question. It's not a fundamental restriction. Okay. So now we have basically this two-leg ladder with one spin chain and a parallel fermion chain and these particular plaquette interactions on it. And the second twist we apply, which is the more fundamental one, is that we wrap this clock onto itself. Okay, we make something that looks more like a wall clock, like the one on the wall there. It's actually a circle. Okay, the clock hand can start from some position, it can go around, and it can return to that initial position. Okay. Notice in Kitayev's construction, this clock was open. There was an initial state of a quantum computation, and there was a final state, which was what you wanted to get out of a quantum computation. Okay. So now here we have dropped entirely that term that gave us the initialization of the computation. We have replaced it with one more of these constraints that enforce a relationship between these different clock positions. Okay, so now the clock can go from here to here, and there is one more of these energetic constraints on that transition. Okay, so now what this does is that it leaves this state psi of 0 in the history state completely unspecified, okay, except it demands this self-consistency condition that it has to be obtained from the state at n-1, kind of what was previously the final time, by the application of one more gate. Okay, so if there's one more constraint, we can iterate it. Okay, so we take the psi of 0 state is related to psi of n-1, which is related to psi of n-2. We can iterate this all the way back around the clock till we return to psi of 0, okay, which happens after one kind of complete cycle backward, and we end up with this product of all the gates. Okay, so this circuit, this capital U, is a circuit that acts on the entire quantum computer. Okay, and so what do we have here? We have a Hamiltonian that is trying to enforce a time periodic computation, saying, I don't know what the input state is. I want it to be the same as the output state. That's a bit unusual in quantum computing, but it is very standard in a different field, which is Floquet physics, the physics of periodically driven systems. Okay? So what we have here is a so-called Floquet eigenvalue problem. It's just a question of what are the eigenstates of a many-body unitary operator. Okay? So claims now. The claim is that the eigenstates of this static local Hamiltonian, this Feynman-Kitaev clock with periodic boundary conditions, are actually related in a way that I'll make precise to the eigenstates of this Floquet unitary. Okay, this many-body unitary operator acting on the quantum computer. And the second thing that is obvious to people who have thought about Floquet systems, but not to others, is that the eigenstates of these Floquet unitaries are highly entangled, and you end up inheriting that entanglement in your Hamiltonian eigenstates. Okay, so let me explain that in 10 seconds. Okay, so the idea is that think about this this clock walking around the qubit register. Okay, and you imagine starting it out in a very low complexity state. Imagine starting it out in the all 0 state, where all the spins are just pointing up, let's say. As the clock hand moves, it applies gates to that register. Okay, and that ends up entangling and scrambling the state of those qubits. Okay, so as the clock hand moves, it leaves behind this trail of entangled states, and when it completes a loop, it's like we have, stirred the system, created correlations, created entanglement, added entropy. Okay, so the question of a Floquet eigenstate is the question of a state that is physically unchanged under this process. Okay, a state that doesn't change when you stir it that way, and it's easy to convince yourself that that means that this Floquet eigenstate must be already highly scrambled and highly entangled to begin with. Okay, so doing this doesn't add any more entropy because we are already maxed out. Okay, so this means that Floquet eigenstates are basically all at infinite temperature. Unlike Hamiltonian eigenstates, which can have low energy, high energy, different quantitative behaviors, the eigenstates of these periodically driven systems are essentially typically at infinite temperature. Okay, So that's the property that ends up giving us high entanglement in our system. I'm going to quickly walk over the how we solve this problem, because it's kind of simple and maybe conveys some intuition. Let's consider taking a state of this form where the clock is initialized in the 0 position and the quantum computer is initialized in one of these Floquet eigenstates. Okay, any state phi that is invariant under the action of the unitary up to picking up this phase into the I phi. Now, what happens as the clock hand moves through the system? Well, we start out from here, okay? So the clock is in 0 and the quantum computer is in state phi. As the clock hops forward, we have to apply this gate to the state. Okay, U0 is this gate over here, acting on qubits 0 and 1. We hop again, we have to apply a second gate, this one, okay? And you can see what happens as you keep hopping forward, okay? We end up, after completing the whole cycle, we apply the entire circuit to our state, and by definition, this circuit acts trivially on that state, just spits out that phase, okay? Turns into a phase factor. That means that after completing this loop, we are back to the same state we started from, which in jargon means that we have a Krylov sector that is closed, okay, not important. But that physically looks like a simple quantum walk on the circle with a so-called Aharonov-Bohm flux, which is just the phase you pick up when you loop around, that is given by the Floquet eigenphase. Okay? Whichever one you put in there works. They all work just fine. They give you different fluxes through this circle. Okay. So now we know how to solve the simple quantum walk on a circle. The eigenstates are plane waves. So e to the I momentum times position, right? And then we have to twist the momentum by this Aharonov-Bohm flux to make it work with that boundary condition. So these are our, I claim that these are our eigenstates for that many-body Hamiltonian. They all look like this. They're specified completely by a momentum for the fermion and an eigenphase for the Floquet unitary. Okay. The spectrum looks like this. It's simply the spectrum of the quantum walk. So it's a cosine of the momentum. Okay, so it's this kind of dispersion law here. Notice that we have this Floquet eigenphase in here that shifts the momentum a little bit. So if you're asking, for example, about the energy gap of this problem, which is very interesting, you're looking down here, okay, very near the ground state. If you expand this out, you find that this gap is basically the square of the gap in the spectrum of the Floquet operator, which is tiny, super tiny, because these level spacings in the Floquet operator are typically 2 to the minus n. And so we end up with a gap of 4 to the minus n, which I think is the smallest gap I know of, like anywhere. It's an extremely fragile construction, okay? But that's not the point. The point is that the eigenstates are very interesting. And in fact, as you can see, packaged within them is this Floquet eigenstate that has a lot of entanglement, this very complex many-body state. Okay. Yes?
Well, quick question. Are you imagining phi is a one-dimensional state if it's a lot of entanglement?
Yes, it's an eigenstate of the unitary, so it's typically some.
So the entire system is a two-dimensional system.
It's just one dimension, right? So it's on a circle.
But phi is a state on the circle?
Yes, on a spin chain with periodic boundary conditions. Exactly. Exactly. So the qualitative picture we end up with is the following. Okay, we have this local static Hamiltonian, okay, specified in terms of some gates, okay, but those gates are local. But everything that appears in Hamiltonian is perfectly innocuous and local. But in solving it, we end up with the eigenstates of this unitary, which is a product of all of these local gates. Okay, so now we get a many-body unitary, but notice crucially, this doesn't appear anywhere in the Hamiltonian as such. The Hamiltonian is local. Okay? And the point is that because these eigenstates contain within themselves the Floquet eigenstates of this unitary, they inherit their infinite temperature-like properties. In particular, this extensive entanglement, which is not rainbow-like, but really it's hot in some sense. It's the entanglement characteristic of highly excited eigenstates. Okay? So you can picture the sort of visually, you can picture the states as, you know, they live on this two-leg ladder. The clock leg of this ladder is what stores all the information about being at low energy. It knows that you're at low energy in some sense. Okay, so this is where the cold aspect of this ground state lives. But the quantum computer actually, so the qubit chain of this, the qubit side of the system is basically at infinite temperature, and it contributes this extensive amount of entanglement, which you can see if you take the entanglement entropy of any contiguous subinterval of this ladder. Okay, just the spin chain contributes an extensive entropy for any one of these intervals. Okay, so formally we have this statement again. It's what I just said. We can lower bound the entanglement entropy of any one of these subintervals, at least for any sort of constant length in general, with a physical assumption, okay, which is precisely this Floquet, the nature of these Floquet eigenstates, which is in jargon called the Floquet ETH. ETH stands for eigenstate thermalization hypothesis. It's the statement that these eigenstates should have local expectation values that are all consistent with infinite temperature, meaning very, very small. Okay, these eigenstates should look very random. In particular, diagonal matrix elements of any local operator should be exponentially small in system size. Okay. Now, this is a physical assumption, okay? It's a very widely believed, thoroughly numerically tested assumption, but nevertheless, it's an unproven physical assumption. And to make this more palatable to mathematicians and get this in QIP and whatnot, we try to really prove everything, with no physical assumptions. And that requires finding a family of unitary circuits that have a provable Floquet ETH. We don't need to assume anything, we can prove it independently. We do this using another idea from computing called linear feedback shift registers. Am I doing on time? Perfect. Yes. So rather than telling you what they are, I'm just going to show it to you. This is what a linear feedback shift register is. Okay, so as you can see, it's a register of bits. Okay, the shift is, as you can see, the bits are getting shifted forward. There is an output bit that gets fed back into the input with some linear feedback from the other bits. Okay, so these bits are getting XORed with some of the bits present in the register. That's the linear feedback part. Okay, this is a linear update on that bit stream that, if you set it up correctly, is going to loop over all the states of that bit string without repeating until it gets through all of them. So this one has 5 bits. It would cycle over all 31 states except the 0, 1. The 0, 1 is always trivial because this is a linear update, so 0 is kind of trivial. But all the non-zero states loop into each other before repeating. Okay, so these are used. This is kind of a very cheap way of getting not very good pseudorandom numbers, but nevertheless, because it's so cheap, it's very common in sort of classical pseudorandomness, and if you enrich it a little bit, you actually can get some secure pseudorandom numbers on this. Anyway, so this is what we are going to use for our construction. How do we use it? Well, first of all, notice the following. The nature of these classical circuits is actually very directly amenable to our construction. So these are implementable as staircase or sequential circuits of swaps and control NOT gates. Okay, so you look at this circuit where the X here is a swap gate. It means it's actually exchanging the states of those 2 bits, and then we have C NOTs. We get this one bit that is sort of going from one edge of the system to the other. That's basically our feedback bit, the one that was doing the loop. All the other bits are just shifting one step in one direction. Okay, so this whole process gives you one iteration of that LFSR, and the C NOTs are doing the linear feedback. Okay, so in the previous animation we had one of them. There could be more. That's not important. So for any given system size, there will be at least one of these choices that gives you one of these maximal LFSRs that loop over all the bits. And that's very nice for us, okay? It means that, okay, because these are reversible functions, they basically split the space of these strings into orbits. And if you choose a maximal LFSR, it splits it into only 2 orbits. One is trivial, it's just the all 0 state. That's always a fixed point for trivial reasons. But then all the other non-zero bit strings are in a single orbit of maximal length. Okay, you visit all of them before repeating. And this is very beautiful because we know how to solve this problem. Now, this is once again a quantum walk on a circle, except now it's a circle in Hilbert space. But we can still solve it with plane waves, okay? We just get an eigenstate that is a superposition over all the bit strings in this orbit, meaning all the non-zero bit strings, with a phase that is just the appropriate unit of momentum here times momentum q times position along the orbit. That's all that is. Okay. Question?
Sorry, the J of Z. Oh, I see. Corresponds to.
Yes, sorry. This is
string
the position of a bit string along the orbit. Thank you. Yes, flash it. So this would pick up a phase of 1. This would pick up a phase of omega squared, omega cubed, so right, and so on. So interestingly, this position of a bit string along the orbit is an object that is independently studied in algebra and number theory, which is it's known as the discrete logarithm of that bit string. This is an interesting function. There are, for example, quantum algorithms for computing discrete logarithms. It's relevant to cryptography and all sorts of things. The property we care about is that it behaves very erratically. It's very unpredictable. If you change the bit string by 1 bit somewhere, the discrete log just changes just catastrophically in an unpredictable manner. You can kind of see this if you look at these bit strings. They're not super obviously ordered in any legible way. Okay, so if you think about it, you can say this is true. So what does that tell us? Well, the eigenstates, as we said, have this form here. Okay, so they are superposition under all bit strings with these phase factors that contain this erratically varying function. Okay? If that was a true random number in there, we would get so-called random phase states that are easy to, it's easy to show they are essentially random states. So as such, they have very high entanglement, they're very complex, all that follows. These are, of course, not true random states. This is completely deterministic, okay? However, there are beautiful results from algebra, from math. We had to scour the literature to look at these old papers about the Riemann hypothesis and whatnot. But this is a problem the mathematicians have studied, and we can use these results to prove bounds on matrix elements of Pauli operators between these eigenstates, okay, using properties of discrete logarithm. And we can prove that all these matrix elements are exponentially small in exactly the way we need for flow kth. Okay, so these eigenstates, completely deterministic, you can write them down, they behave like random states for these purposes. We can also test this bound. We're physicists, so we trust the math, but we also want to see the numbers. And so we churn the numbers and we look at many of the matrix elements, and it's actually quite beautiful. They really hug the bound very, very tightly. So there is really no question that this is the correct bound that we found here. Okay, so this is it. So putting it all together, we can take one of these maximal LFSR circuits, we can plug it into our periodic clock construction, and putting this together, we get this construction of static, geometrically local 1D Hamiltonians, where all the eigenstates, which means also the ground state, inherit this volume law entanglement for all subintervals of the chain. Okay? So they're qualitatively more entangled than rainbows. If you think about a rainbow, you can easily find subsystems that have very low entanglement, and this is not like that. It really picks up this infinite temperature structure from this mapping to flow K. Last thing I want to say is that actually Sam was, I think, going to talk about this, but then changed topics. Anyway, it's Sam and Dima Varin put out this very, very interesting paper a couple of weeks ago that has a title that seems very intentional with what I just said, right? It says quantum matter is weakly entangled at low energies, and we kind of already, we've been talking about something very different. Both papers are correct, okay? But it's interesting to see how they fit together. So what they show in the paper is that they can upper bound the entanglement entropy of some state of some energy by the thermodynamic entropy of the two states you get when you bisect the system by just removing, cutting it in half, removing some of the degrees of freedom. Okay, so there is this idea of a third law of thermodynamics, which is fake. It's not a true law. You can violate it in many ways, but nevertheless, it says that the thermodynamic entropy of a system should go down to 0 as you lower the temperature. Okay, again, not a real law, but it holds kind of quite generically, right? So based on that, you would think that indeed, as I lower the energy of my state, this thermodynamic entropy goes to 0. The entanglement entropy accordingly should also go to 0, right? Or at least to a sub-extensive value. So how does that fit with our construction? Well, we have this periodic clock, okay? To get this mapping to thermodynamic entropies, we have to cut it open by removing some bonds, okay? It's done. And when we cut open the clock, we end up having, we remove one of these constraints, we can put any state we want in the input of our problem, and any one state gives us a valid ground state, so we get this massive exponential degeneracy that makes this all compatible with that result. So it's of course very fine-tuned, but it's an extreme example of how this bound can hold when the third law is violated, let's say. Okay, so concluding, what else can we do with this? I have some exciting preliminary results on spectral form factor, which connects to quantum chaos, and then we can ask a bunch of other questions. But in general, I think this is an interesting model where we can learn some new lessons about many-body physics from taking this, from learning more about quantum information, let's say. Okay, so thank you. I'll take any questions.
Trying to understand why this periodic boundary condition seems to be so essential.
Yeah.
So if you don't have this, you can still construct a Hamiltonian where the gap is exponentially small.
Mm-hmm.
And can it not have such complex entanglement?
Right. So if you open the clock, you get the same history state that I showed. It's just going to be instead of a periodic history, it's going to be an open history. So you start from 0 and you evolve. In our model, this is a geometric local clock. Okay, so the depth of the circuit, the size of the circuit, the number of gates is n. So the states you get in that history state have a complexity of at most that, right? They're not very entangled. They get acted upon. Each bond gets acted upon by exactly one gate. So these will have not very high entanglement, even though they might still have a very low gap. Yeah. So it's really essential to close the boundary conditions to get this mapping to Fouquet problems. I'm not sure who was first.
This connection, I thought it was very interesting that, yeah, like now you talk about eigenstates or, eigenphases of unitaries. And I couldn't help but think for, say, random circuits or, good pseudo-random unitaries, what do we know about their eigenstates and whether they're entangled in this sense, or do you really need something as strong as Fouquet ETH, or do you also believe that the eigenstates of these unitaries can satisfy the properties you want?
Right. So there is we were looking at rigorous results on Fouquet states, for example, to say whether we could say, for example, these ground states are highly complex, let's say. And there is a surprisingly small amount of results in that direction. It will be very interesting to know more about what we can say rigorously about these states. In general, even if you don't have exactly Fouquet ETH, you would inherit a volume law, even if it comes from some other mechanism that isn't ETH, right? So maybe more structured circuits could also give you this. But here we are really looking for this kind of thermal type of entanglement. So we didn't think about that.
Yeah, I think I might have figured it out just by staring at this thing, but can you remind me again what the central message is about why the 1D area law argument doesn't hold in your case?
So this, the proof of the area law in 1D relies on a gap. Right? It says basically the entanglement entropy is bounded above by a log of 1 over gap. Right? So if the gap is constant as the size increases, that is an area law. In our case, the gap is exponentially small. And so you can get this one law. Right?
Is this,
yeah.
So you mentioned you had in the Fouquet systems, you mentioned this lower bound of the entanglement of a subsystem. But you say entanglement entropy is less than or equal to area times log 2. But I would have thought that's just the maximum possible entanglement entropy you can have.
We have 2 chains. So in principle, if you make the clock many-body, the maximum entropy you can have is log 4 per site.
I see. Oh, okay. But I thought this result was where you have what? I thought this result was in the single particle.
It is. So in the single particle, it's really almost maximal. Yeah, you could get log n additive term on top of that from the fermion.
Oh, I see. Okay. Right. And then the point is that if I took Fouquet eigenstates, then the fluctuations around log 2 times area are actually smaller than the additive amount you get from the.
That's right. That's right.
Right. Thanks.
okay, maybe if there's no further questions, let's thank Matteo again.
Thank you, organizers.